Does special relativity allow for faster than light travel? Faster than light travel, FTL travel, is the idea of a body having a velocity greater than the speed light, the recognized speed limit of the universe. We are usually told that the speed of light, c, is a constant value of which massless particles such as photons travel through the medium of a vacuum, such as ideal intergalactic space. It would be incredibly useful to travel faster than light because, for example, the next closest stars in the Alpha Centauri system are roughly 4.3 light years away, which would be an unnecessarily long voyage of 4.3 years for future explorers, even if we could approach light speed travel. Though with such great reward, why hasn't it been done yet? Why do scientists say that it's impossible to travel faster than the speed of light? Is the speed of light really the ultimate speed limit of the universe, in which we will never be able to exceed? Today, we are going to investigate why exceeding the speed of light is deemed impossible by physicists, but to fully understand why we cannot travel faster than light, we're going to need to refer to some of Einstein's greatest workings, the theories of special and general relativity. Let's start simple. Most of us are familiar with Newtonian mechanics, which is the treatment of classical mechanics based on Newton's laws of motion, assuming that distance, time, and mass are all absolute. The fundamental force equation of Newtonian mechanics, F equals ma, is an accurate relationship for the force required to accelerate mass, which for all intensive purposes has been extremely accurate at modeling this relationship, though doesn't account for extremely fast things. Albert Einstein, founder of special relativity, had concerns with these models. When Einstein was 16, he realized that Maxwell's equations of electromagnetism and the idea of the speed of light didn't coincide with Newtonian absoluteness. It was around this time that the famous Michelson-Morley experiment disproved the existence of the luminous ether, that light, in perpendicular directions, traveled at different speeds due to traveling more prominently through a dimensional component of the universal medium than another, which was widely assumed true during the 19th century. But firstly, as a fundamental requirement to explain special relativity, it is important to know what a frame of reference is, and what it means to be in a frame of reference. A frame of reference is essentially a basis of which other objects are measured by. According to Newton, the idea of an object traveling at 20 meters per second isn't necessarily valid, instead followed by relative to. For example, the soccer ball is traveling at 20 meters per second to the right relative to the ground. This, of course, allows for transformations, allowing you to say the ground is traveling at 20 meters per second to the left relative to the ball. Understandably, it is generally assumed that the observer, the frame of which reference is being used, is a person making the statement. For example, a bike relative to us might be traveling at 20 meters per second, though relative to the International Space Station, 8,000 meters per second, all of which can once again be measured relative to the road. Suppose you are in a car traveling 50 kilometers an hour down a straight road relative to an outside observer, and a speeding ambulance overtakes you at 60 kilometers per hour, once again relative to the road. To you in the car, it only appears that the ambulance is traveling at 10 kilometers an hour relative to you, as the displacement between you and the ambulance is increasing at a rate of 10 kilometers per hour. Likewise, to a person in the ambulance, you are traveling at 10 kilometers an hour in the opposite direction. While this idea may seem initially absurd, if you were in intergalactic space and had no intuitive frame of reference other than yourself, that is the Earth, you would only be able to measure this 10 kilometer hour difference, as the idea of you and the ambulance traveling at 50 and 60 kilometers an hour respectively is only valid when measured from the Earth's frame of reference. An inertial frame of reference is a frame of reference that when used as the basis of a measurement, an object at rest or moving at a constant velocity won't accelerate unless forces are applied. For example, if you were in space where the external forces are negligible, and you released a ball out in front of you, the ball would remain the same distance away from you and not accelerate relative to you, thus being in your inertial frame of reference. This also implies that inertial frames of references are the basis of measuring true acceleration, and that an object is accelerating if one can identify an inertial frame of reference relative to which it is accelerating. In Einstein's theory of general relativity, not to confuse the two, Einstein postulates that gravitational and inertial mass are equivalent. This is known as the equivalency principle. Einstein states that an object in free fall accelerating down to Earth at 9.8 meters per second is actually inertial, and the Earth is instead accelerating up to the object at 9.81 meters per second. Hear me out. It was Newton that defined an inertial frame of reference to be the basis of which true acceleration is measured, and also stated that an object is accelerating if you can identify an inertial frame of reference at which the object is accelerating. Einstein saw the loophole here, and suggested that the idea that the Earth is accelerating up to the object is consistent with Newton's claims. Say you were falling from a plane, though you were contained inside a box with a ball. You and the ball both free falling at the same rate, and if you were to let go of the ball, it would remain stationary. It would be indistinguishable to outer space, as you nor the ball are able to observe the effects of gravity inside the box, and because this is consistent with the idea of being an inertial frame of reference, the Earth must be accelerating up towards you. While developing his theory, Einstein also realized that spacetime must be non-Euclidean, that is, not flat nor linear, as spacetime isn't absolute, and that mass distorts the shape of spacetime, described by Einstein's field tensor equation here. Objects, therefore, in freefall, accelerating very slowly radially inward due to Earth being round, is just a consequence of Earth's mass distorting the shape of spacetime around it, and that these straight lines only resultingly appear to be curved. Back to special relativity. At this point, Einstein's theory of special relativity consisted of two main postulates: that the speed of light in a vacuum is constant for any frame of reference, roughly 300 million meters per second, and that the laws of physics are the same in all frames of reference. We will see how the second postulate is also so important later on in the video. In order to start performing transformations and doing relativistic calculations, it is necessary to understand how relativistic space-time diagrams work. For this, let's go to Desmos. In physics, the convention of a space-time diagram is to graph the x-axis as space and the y-axis as time. We will only be concerned with one spatial dimension and one time dimension as to simplify things for a two-dimensional graph. Let's say this is you as you move forward in time. That is, progress through the y-axis, and you are relative to yourself are not moving, and therefore have a velocity in your frame of reference of 0. Let's say you throw a ball and it moves away from you at a constant velocity of 1 meter per second. This can be modeled by y is equal to x. So far, this is all just graphing what we learnt in Newtonian high school physics. We see that when t equals 1, that is 1 second from the origin, the ball is 1 meter away from you. After 2 seconds, it is 2 meters away from you. We can now do a translation to see what my velocity looks like relative to the ball. It looks like we are moving in the other direction at 1 meter per second. After 1 second, we have traveled 1 meter to the left relative to the ball. After 2 seconds, 2 meters to the left relative to the ball. Although at this magnitude of such small velocities, this is essentially correct, this is technically an inaccurate transformation relativistically speaking that requires a little more complication. Bear with me. The speed of light is constant in all frames of reference. So for ease, let's make the x-axis 300 million meters and the y-axis 1 second. This is so that when we want to model light, it can be at a 45-degree angle and modeled by y is equal to positive or negative x. Now let's have you once again sit at the origin and throw a ball at a really fast speed so we can observe the effects. We see the ball fly away at half the speed of light. Y is equal to v over c times x. You might be realizing that if we do this transformation that we applied before, the speed of light fails to remain constant, and this is a huge problem. Luckily, there is a new type of transformation that can also preserve a particular axis, which we will assign to the constant speed of light. By squeezing the 45-degree axis on the right and stretching the 45-degree axis on the left, the speed of light remains the same, and now you are traveling relative to the ball at the same speed, though in the other direction. Notice no matter how much we squeeze or stretch this grid, it's impossible to transform a velocity to that of the speed of light. It simply approaches it. To exceed the speed of light, since it's unchanged in this transformation, would require some sort of flipping or change in how these lines are ordered. which is clearly impossible. It's slowly becoming apparent now that no transformation can result in a velocity exceeding the speed of light. Therefore, a velocity of an object relative to anything else cannot be observed to be going faster than the speed of light. The speed of light cannot be exceeded. If you're not satisfied with the intuition of not being able to travel faster than the speed of light yet, stronger arguments are going to be covered soon. Here is a more advanced tool, which I found on Reddit and didn't create, that allows us to visualize how events can transform in spacetime the same way. Fun fact, the shape is also hyperbolic. But anyway, we can see using this tool that events we observe happen at set intervals. We observe them happening at different intervals for any events with a velocity. They are more spaced out and therefore it would seem time is traveling slower for them. This also comes with a consequence that two independent frames of reference won't necessarily agree on simultaneous events. The famous analogy goes, if you were directly in between two lightning bolts, you would experience the events happening simultaneously. As the events happen from equal distances away, the light travels the same distance to get to you. However, if you are on a train moving away from one lightning bolt and closer to the other, it would appear that the one you are moving towards happened first, followed by the second one that you are moving away from. In fact, if you were inside the train and somehow able to travel faster than the speed of light from the lightning bolt behind you, you would never observe the event occurring unless you slowed down and gave the light a chance to catch up. I wish to emphasize that this is impossible using relativistic principles. This analogy describes how two observers in different frames of reference won't necessarily agree on simultaneous events, or in the order at which events happen, as the speed of light is still constant in all frames of reference. Here is another intuitive analogy that leads up to the next topic. Suppose you're on a train moving at 80% the speed of light and shine a torch forward. To you on the train in an inertial frame of reference, only see the photon shoot out the torch at the constant speed of light. However, from the frame of reference outside the train, that is, someone outside the train watching this event take place, what do they see? Do they see a beam of light simply traveling forward at 180% speed of light? Well, no. This is because relativistic velocities simply cannot add together anymore. We can, however, do transformations to understand what's going on. As in the spacetime globe, we see that when we do a transformation from the outside observer's frame of reference to the person inside the train's frame of reference, the speed of light is still, you guessed it, the same. A final point to make is that the space and time are more similar than you may think, hence the single word space-time. As a matter of fact, relativity considers it the same thing, which is why spacetime manifolds are named spacetime manifolds. You can say that school is 5 minutes up the street from your house, even though it's a distance. It's the time it takes for you to get there. Likewise, we can now start measuring time in meters, as it takes light 1 second to travel 300 million meters. The y-axis is therefore going to be referred to as ct, light multiplied by time, which is simply rearranging velocity is equal to distance over time to velocity time is equal to distance, or as ct puts it, in meters. With this diagram, we can now fully observe the phenomena known as time dilation, that we observe time for objects moving relative to us appear to progress slower and vice versa due to the change in frame of reference, because we can also be the one moving with a velocity relative to the other object. The following argument is going to be the first true reason we see in which no spacetime entity can traverse through space at a velocity greater than light. A postulate of general relativity is that we all spacetime entities are traveling through the spacetime manifold at light speed, and it's just the component of which we are traveling in that's changing. Most of us are traveling primarily through time and little through space. Once again, this is all relative to each other. Though, if something is traveling at a relativistic speed relative to you, the observer, we see them expending so much more of their light speed through the first 3 dimensions that they are now traveling slower through time as a result of their light speed vector being more aligned to their spatial components. And this is why the time component of the 4-dimensional manifold is receiving less. That is, time dilation. A better way to visualize this is if we have a meter-long ruler on a Cartesian grid. Parallel to the x-axis, it looks a meter long, though when we rotate the ruler, the x component of the ruler is no longer a meter. but the ruler just hasn't simply changed in length, it simply comprised less of the x component and some now of the more y component. The only difference is that the ruler is the speed light, and one axis here is time, while the other three, or one in this case, are spatial. We can see that no matter how you align this light speed vector to the manifold, it's impossible to exceed the speed light in any direction, as being perfectly parallel to a spatial component of this manifold only allows you to travel at the speed of light through space. No transformation can be made to align your vector to be more parallel to any axis than perfectly parallel, and since the speed of entities through the spacetime manifold cannot fundamentally change, it is impossible to exceed the speed light in any given dimension. Not only is this a shallow proof that the speed light cannot be exceeded, this also gives an intuitive sense on how time dilation works and how light could possibly seem to travel slower for things at velocities relative to you, because the time component is simply being expended to increase the displacement between you and the object over time. That is velocity. When I was learning about special relativity, I had difficulty understanding how two objects with changing distance between them could observe each other to have slower time. But this is simply a result of the postulate mentioned earlier. The laws of physics are the same in all frames of reference. This is a residual effect, how each frame of reference in this case is inertial, and how the other frame of reference is the one that seems to be moving away. Another time dilation analogy goes, if you are standing and someone at rest shines a laser at a mirror, we both observe the laser to go in a straight line to the mirror and back. However, if this person has a velocity, such as being on a fast-moving train, they see the light shine from the torch to the mirror as they did before, although the speed light is the same in all frames of reference. Since we are observing the light to travel forward while moving, it is going to be traveling in a triangular direction at a constant velocity c, thus taking a longer period of time for the light to bounce back to the person on the train. Likewise, this person sees themselves at rest and you moving, and therefore would experience the same phenomena if you had been the one shining a laser into a mirror. Soon we will see how a paradox not paradox confuses some special relativity newcomers. With this clarified, we can now understand how this can start to get complex, understanding how relativistic transformations work, but we are getting there. It turns out an object with a velocity relative to an observer experiences two phenomena, time dilation and length contraction. Length contraction, the second important phenomena, can be thought as a time dilation spatial counterpart. As we saw how moving objects experience observed time slower, they also appear literally shorter in length. If we assign a distance to something and then send it to the right at a velocity relative to us, and then apply a transformation, say, to someone on the left, we see that the distance is physically shorter when compared back at the same time.
Now that I've covered most of the intuition behind a Lorentz transformation, let's go over some of the algebra. And I'm going to be doing this on paper because I find it just so much easier than on a computer. May I just quickly point out how hard it actually is to record this? Because I'm doing it one-handed. I don't have a tripod or anything. So it's going to work. It's going to work, okay? Don't worry about my messy handwriting and don't worry about my mispronunciation of words. Because C is always greater than V, but physics is always greater than English. Just remember that, okay? Yeah. So what do we know about just transformations in general? Let's go to Galilean firstly. So here's our space-time globe. Let's say an event happens here. For us, we see that it happens at some x value in meters away from us, and let's just say time for now. So it happens after time, seconds, x meters, to a friend going relative to us. They see it happen at the same time, but a different x. They see it happen at this x. And we can find this displacement by subtracting off this distance here, which is going to be velocity times time. That's the distance there. So x prime is going to be equal to x minus velocity time. And we can say the same argument about them. So if the event happens here for them, we're actually moving this way. And you can use the same principles here, and we find that x is equal to x prime plus vt prime. But we know this is wrong, because if we've got the speed light here, we're now observing the speed light at two different speeds. We know that it's constant, so the only way to keep it constant is multiplying this by a scaling factor. We call this gamma. I've done this quite messily, but gamma multiplied by this. Let's make that a bit bigger because it's not subscript or anything. Gamma, okay. So, when we observe the speed of light, this is any one because the speed of light is constant in all frames of reference. It happens at when x is equal to, we're going to start calling this ct now. It happens when ct is equal to x because the speed of light is observed to go at a 45-degree angle. So we can say that ct is equal to x for events that happen at the speed of light. And we can use this to help us derive gamma, but we'll get to that in a bit. Okay, so we want to derive gamma from these two models, so let's multiply them together. Prime is going to be equal to, we've got two gammas, so gamma squared, and then let's FOIL it out. So x prime, x prime, this times this is plus x vt prime minus vt x, that's going to be minus x prime, and then last minus vt prime. Okay, and since we saw up here ct is equal to x, ct prime is also going to be equal to x prime because the speed light is constant in all frames of reference. So no matter whose frame of reference you're in, we always see that ct is equal to x. So this means we can start substituting in ct for the x's. So ct prime is equal to gamma squared still, ct prime plus ct vt prime minus, I'm going to do this first, ct prime vt minus vt prime. And this is ct, we can say ct, and we've got vt prime, so these terms are pretty much the same, they're just written differently. So we've got plus that and minus that, so they cancel. So now let's start simplifying things again. C squared t prime, just combining the c's, is equal to gamma squared, let's do it again here, c squared t prime, and then minus v squared t prime. Okay, what do we see here now? We've got tt prime in, we can cancel out tt primes now because this is multiplied by this, multiplied by this. All the terms have tt prime, that we can cancel out. So that means c squared is equal to gamma squared of c squared minus v squared. We want to find out what gamma is, so we can divide both sides by this here, so we get gamma on one side now. So I'm going to write gamma first. is equal to c squared over c squared minus v squared. And now on this side, we can divide everything by c squared because, well, I see that that can cancel with that and then divide that. So gamma is equal to, that's going to be 1 over 1 minus v squared over c squared. My bad, this is still squared. Okay, so this is going to be equal to, we want to find gamma now, so this is going to be equal to the square root of the top, which is square root of 1, still 1, but now the square root of the bottom is 1 minus v squared over c squared. And we're done. Also something I accidentally forgot to include. Now that we know this is gamma, we know that x prime is going to be equal to gamma x minus beta ct, and ct prime is going to be equal to gamma ct, notice the symmetry here, bx, and, well, b is beta, but I don't know how to do beta, so let's just do b. B is equal to v over c. And if you notice, if v were to be equal to c, beta is going to be 1. And also down here, if v were to equal c, such as you're trying to do a transformation to someone moving at the speed of light, it's going to be 1 minus 1, which is 0. Square root of 0, you can see where this is going. 1 over 0, it's not going to work. This is going to be undefined, meaning this transformation cannot take place. And if v is greater than c, then this is going to be a negative denominator, so this factor here is going to be negative. And what this would look like, if I were to just draw this real quick, here's the speed of light, here's usually their time and space, but if they were to be going faster than the speed of light, what this would look like is that their axis now invert. So this is ct prime, this would be ct prime prime, and this would be x prime prime. It would look like their axis or axes have now inverted because they've exceeded, well, this is now negative. They're doing what isn't meant to be possible, and it's not possible. You can't go faster than the speed of light. And what this would imply, if you were somehow able to achieve such speed, it would look like you're going backwards in time now, because this is just reversed space and time, and events would be parallel to this axis, so it'd be going down this way, and you can just see that this isn't going to work. Events are going to happen back in time for them. Not possible.
Let's do a few examples. I shoot a laser and the photons travel out the laser at the speed of light. The event of the photons passing through 1, 1 obviously happens at 1, 1 for us. That is, we saw the event happen in 1 second at 300 million meters away. But what does our friend traveling at half the speed of light relative to us see? Well, let's plug in 0.5 c as the velocity. This turns out to be approximately 0.577, 0.577. That is, they saw the event happen at 0.577 times 300 million meters away at a time of 0.577 seconds. If you wanted to be conventionally correct, you'd say this happened in 0.577 times 300 million meters instead of seconds away. Let's do another example. I have two friends this time, let's say Ash and Ben. We all begin at the coordinates 0, 0, and Ash is moving at a fifth of the speed of light, and Ben is moving at 3/5 the speed of light through intergalactic space relative to me. Let's say event A for Ash happens for what we observe to be at 0.2, 1. We want to find out how Ben experiences this event. This point is beyond the inside of the skew now, But that doesn't matter, as like any Cartesian grid, can be in a different quadrant from the origin. To find the value of t, we go parallel to the t prime axis, and to find the value of ct, we go parallel to the ct prime axis. Plug in the values, 0.6 is the velocity. Ben sees this event happen at 1.4. You can see the problem with these transformations when we pose the idea of observing a greater than light speed. As time starts to dilate and length contracts more and more as the two axes converge at relativistic speeds, given by the relationship we saw earlier, it seems illogical to achieve a velocity of light, as in time would start to dilate to infinity, and length would also infinitely contract. If we continue and make v greater than c, we see that space and time axis invert. We can prove this as the equation for y is v over c x. The angle produced is arctan v over c. When v is greater than c, the arctan input is greater than 1, and when computed is greater than pi over 4 radians, which is the angle of the speed of light. This is the same as plotting inverse, which is similar to plotting in the negative direction of the origin on regular axis. This means that faster than light travel implies that the flow and direction of time would be inverted, and you would essentially witness an object travel backwards through time, with a negative length. This not only shows us that observing a velocity greater than light is illogical, but also shows that traveling back in time would also be impossible. This translation, that has worked countless times, theoretically and experimentally over the past 100 years, shows that the speed of light cannot be exceeded using the principles of special and general relativity. Now let's think of how adding velocities together may work, as it should be well apparent right now that you cannot simply add relativistic velocities together, as this would most likely exceed the speed of light.
So I'm a little sick here, but we're going to now derive Einstein's velocity addition formula. So say this is you in your own frame of reference, and we see some object traveling this way with a velocity v, and we've got another object here traveling relative to us with velocity u, and we're just going to say that because we know velocity is the same as change in x over change in time, that's displacement over time, that's what velocity is. And what we want to know is, how does this observer here see this person's velocity, okay? So what we're really asking here is, if we do a transformation to this person, how would they see the velocity of u? So this is going to look like change in x prime over change in t prime, okay? And we recognize x prime because, as we saw before, we can do a transformation to get to that. And by adding change before the x, we're just going to add change before the other variables. Let's just see what that looks like, okay? So we've got change in x, change in x prime is going to be equal to, this is nothing new here, gamma change in x minus beta change in ct. All I've done here since the last Lorentz formula was added change. But we want to know, what is that over change in t? So we're going to find out what change in t prime actually is. Well, we don't know change in t prime, like right off the bat, but we know that change in ct prime. Okay, so before we start throwing variables around the room as if they mean nothing more than a Greek letter, because honestly that's what algebra makes us do, let's just think about what change in ct prime actually represents, okay? So in this case, the delta is going to be commutative because c multiplied time is going to be some fluctuating value. But this is also going to be equal to c change in t prime. And one really good way of understanding how this could work is that what does this actually mean? What is the change in C? You know, like, what are you, Isaac Newton or something? No. The change in C is just a meaningless thing. It is look, change in C makes absolutely no sense. This has got to be the stupidest thing I've ever seen. It's really the change in T prime which we care about, because T prime in this case is what's changing. So since this visually makes a whole lot more sense than that does, we're going to start using this from now on. It is equal to gamma C change in T, which remember is that's minus beta change in X, okay? And what we can do here is we want to get rid of C, because if we go back over here, this is really the same thing, but it just doesn't have that C at the start. So let's start dividing things by C. So this is going to be equal to, if we divide everything by C, it's going to be change in T prime is equal to that gamma, and C over C is just nothing, so change in T minus beta is V over C, so that if we divide it by C, it's going to be V over C squared change in X. So let's put this over here. It's going to be equal to that gamma, come on, focus please, change in T minus, that's horrible, V over C squared change in X. And now gamma is going to cancel out because the numerator and denominator both have multiplied by gamma. And now what can we do, okay? You might notice that every term here, 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 and here is either divisible by t or has a change in x in it, which when divided by change in t is going to result in looking as u. So let's do that. Let's divide every term by change in t, okay? So that's still equal now. Actually, I'll move down here, more space. So change in x over change in t minus, this is minus bc change in t, so that t is going to cancel out. So that's just going to be, well, actually, let's work this out. This is going to be minus beta c, which is vc over c, which is just going to be minus v change in t. And since we're dividing it by change in t, that's just going to be minus v. So all that simplifies down to minus v. Now let's put that over. What's change in t over change in t? That's just 1. Okay. And then what's this over change in t? Well, since it's multiplied here, I just put minus v over c squared times change in x over change in t. We know that change in x over change in t is u, which is why I've written it like this. That's going to be u minus v over 1 minus, let's see what we can do here. So this is going to be u, so vu over c squared. And now we are done. So where u is the velocity of this ship, or person or whatever. V is the velocity of this one here. And yeah, that's the derivation. As a quick note, notice the difference between the formulae we are using to transform to u prime and back to u. Earlier we derived the formula on the left, however both can be derived the same way, and it depends on the problem as to which formula you're going to want to use based off which frames of references you're given. In the following examples, we're just going to be using both of the formulae to get familiar with them.
Notice how if we start plugging c into v or u prime, or both, the result is always c. The speed of light relative to the speed of light relative to an observer is the speed of light, because the speed of light is the same in all frames of reference. Even if you start chucking random values of v and u prime that are greater than c, you still cannot add velocities together to exceed the speed of light relative to an observer. Intuitively, this would be because time would dilate so extremely that it would go backwards, although this isn't super important because exceeding the speed of light is impossible. We can see that adding relative velocities will never exceed the speed of light, not even if someone traveling at 0.9 c relative to someone traveling at 0.9 c relative to someone traveling at 0.9 c traveling relative to someone at 0.9 c relative to you still wouldn't observe the guy at the end traveling faster than the speed of light. If you try to reverse and engineer this equation, setting u to something greater than 1 and substituting v and u prime for x and y to attempt to find solutions for this, we see that no solutions exist for u to exceed the speed of light when u prime nor v are greater than 1 themselves. That is, two velocities between -1 and 1c added together cannot exceed the speed of light. Since transformations can be made on objects moving at relativistic speeds, we furthermore see that exceeding the speed of light by traditional means of special relativity is impossible. Let's do some examples of this to understand the formula. Consider Ben is moving at 4/5 the speed of light relative to Ash, and Ash is moving at 3/5 the speed of light in the same direction. How fast do we see Ben moving? Newton would say 7/5 the speed of light, but that's clearly wrong. So let's plug 4/5 and 3/5 the speed of light into the formula to find u. This comes out to be roughly equal to 0.946 the speed of light, meaning that Ash is observing Ben at 0.8 c, and we are seeing Ash move at 0.c in the same direction. We therefore see Ben move at 0.9459 c. Let's try another example. Say we observed Ben moving away from us at half the speed of light, that is negative 0.5 c, and we are observing Ash moving away from us at 0.9 c. This time it might feel like Ash and Ben are approaching each other at 1.4 c, which we know is wrong from their perspective. So let's calculate, this time from u prime. This turns out to be 0.965 c. Neither of them observe each other nor anything else in the universe to be traveling faster than the speed of light. You might think the applications of this are limited, as on Earth we aren't ever close to relativistic speeds, though it has a noticeable effect and more common than not, because the Earth's position is far from absolute. The Earth is orbiting the Sun, which is orbiting around a black hole inside the Milky Way, which is flying through the universe relative to other galaxies. So Earth's velocity changes tremendously depending on your frame of reference, and relativistic velocity addition on such a large scale becomes a macroscopic factor when calculating almost anything intergalactic. Some students fail to understand how important relativity is in physics and the practical world. Trying to calculate intergalactic travels on scales much larger than outside our Earth with Newtonian mechanics is like trying to calculate the physics for a car with negligible friction, or a plane without air resistance. Or sometimes it's even more crucial and can make a difference between GPS functioning or failing. No matter how fast a large object may be traveling relative to another fast object, we will never see them travel faster than light relative to each other. Not by shining a laser on a train, not by ejecting matter from a spaceship traveling at a relativistic speed, not even Earth spiraling through space relative to a star in the Andromeda galaxy. It might seem at this stage that we have simply abolished everything we know about universal constants and replaced it with only the speed of light being absolute, a downgrade to say the least, though there are a few more things to mention as this isn't over yet. Remember how Einstein said that the laws of physics are the same in all inertial frames of reference? This means that there must exist a true length and a true time for any event, that is, the event experienced from the frame of reference that's inertial to. And to find this, you can either perform a transformation from a frame of reference to the inertial frame of reference, or calculate it using a Pythagorean theorem after a Lorentz transformation. This means that for anyone or anything traveling relative to you at some velocity would experience your events to happen, of course, differently, although no matter their velocity, they are always able to perform a transformation back to you to understand how you are seeing and observing everyday life. And this is something that every frame of reference in the universe can agree on. The event relative to another defined frame of reference, typically the principal frame of reference being that of the events at which true distance and true time of the event are measured by. There is a final paradox that may seem to arise when earlier I said that frames of references moving away from each other experience each other to have slower time. Although this is true, it allows for a seeming loophole known as the twins paradox. If your twin were to leave Earth, fly to a distant planet at a relativistic velocity, then come back, who would be older, as we both experience each other to be younger? However, this isn't actually a paradox at all, and can be fully resolved intuitively. Firstly, imagine a Lorentz transformation to your twin who is traveling away from you. Their time axis will be skewed. However, at some point your twin must turn around and come back home, at which point his velocity changes all the way to the other direction, which must not be modeled by the same Lorentz transformation, instead a separate one. This skewing of the lines is not accounted for in the paradox. Furthermore, since a velocity cannot instantaneously change, your twin must start accelerating in the direction in order to come back to you. This, of course, takes some amount of time, which when modeled by world lines, returns a messy non-Euclidean map of their experiences of time relative to you back on Earth. Since the forward and return journey of the twin are skewed in different directions, we observe the twin to experience less time than us from the twin's point of view. Their acceleration actually accounts for the time which makes up on Earth as a period as it should. Therefore, in conclusion, to clarify the paradox, we observe the twin is younger and having less time pass for them as did for us back on Earth. This is the majority of the introductory content into special relativity, although before wrapping up it is important to quickly investigate how this all impacts Newtonian mechanics, because after all this was in retaliation to most classical Newtonian formulae. E equals mc squared is one of the most famous equations of physics that relates mass and energy, and fortunately this comes in handy here. The math gets rather complex, but the formula states that the mass of a body isn't constant, especially when moving at relativistic speeds. The full equation for this involves advanced calculus and vectors and tensors in 4 dimensions, and relativistic momentum, which is outside the scope of this investigation, but essentially we can see that the mass of an object traveling relative to us increases as the velocity increases, as it has increased momentum relative to us, therefore energy, therefore mass. This happens to tend off to infinity as it approaches the speed of light from our frame of reference, as it is once again consistent with the fact that nothing can travel faster than the speed of light. This applies to all mechanical physics, and when done so, it is certain that nothing with mass as we know it can equal nor exceed the speed of light, not by force, acceleration, centripetal force, addition of velocities, massive collisions conserving momentum on small particles, not by transforming, not even with almost infinite energy,
Not even the speed at which you got to fly to school at 9 a.m. because you slept in and you're now late.
as the hyperbolic nature of our universe just doesn't allow for it. You can stop asking. Einstein truly has revolutionized physics.